It should take a second to open up. There you go.
Good morning, everyone. So welcome back. Today we start again with a keynote speaker for both events, the DataFest and the ComputeFest. And to introduce our distinct speaker today, I'm going to let Alyssa Goodman, my colleague friend from Astronomy Department at Radcliffe, to introduce the speaker. Please.
As you can see, our honored guest, Fernando Pérez, is standing here eager to go. So I'll be very, very brief. So many of you, I'm guessing all of you, I won't even ask for a show of hands, know about Jupyter environments and probably know that that came from IPython and may or may not know that that came from Fernando, who will tell you that it came from Fernando and his friends, which is true. But as far as I understand it, he was a graduate student in Boulder in physics and didn't like the messy software stack that he was forced to use and decided to clean it up and spent, what, 6 weeks writing the first version of IPython, something like that. And then since then, he's founded this amazing Jupyter organization that we're also familiar with. And I just want to say that I only recently realized that other than Jupyter being misspelled, it does have a connection to the planet Jupyter in that one of the things I show when I give visualization talks all the time is the page of Galileo's notebook that mixes figures, little drawings of Jupyter and its moons with text, with Galileo's mental math, shall we say. And that is the precursor of a Jupyter notebook. And isn't that adorable? And I bet half of you didn't know that. Okay, so there's my factoid for the day, and I should tell you that, of course, Fernando has many academic credentials. He's currently an assistant professor in statistics at Berkeley and has many other affiliations having to do with data science and Lawrence Berkeley Labs, and you can see all of that on his website because he and I are both eager to hear what he has to say about Jupyter meeting the Earth, and this is very much Jupyter with a Y. I can tell you as an astronomer that Jupyter with an I meeting the Earth would be a big problem. So thank you, Fernando.
Thanks, Alyssa, for that kind introduction, and to the organizers for having me here. I apologize in advance if I start coughing. I have this TB that's turning into a cold, and it may happen more than once during the presentation. Alyssa's completely right. In fact, the logo for Jupyter is what happens when you feed the original drawings, hand drawings of Galileo to a graphics designer, and we worked with a designer and with a team to effectively kind of abstract and modernize it. The moons are obviously on the plane, and we moved them we took some artistic license to make something that would be square, that would fit on a sticker, that would fit on a website. So there's some artistic license, but that logo actually is effectively a simplification and an abstraction of Galileo's original drawing, and that's what motivated it, taken from the Sidereal Messenger actual pages. So yes, those images that Alyssa uses were the ones that we had when we announced the new project Jupyter back at SciPy 2014 when this came out. So, and the connections to astronomy in the birth and growth of the scientific Python ecosystem are many. But today I want to talk a little bit about its connections to earth sciences. I want to credit my co-author, geophysicist Lindsay Hagee, who works with me at Berkeley, I'm sorry, with whom I've developed a lot of these ideas. A teeny bit about my past, as Alyssa mentioned. I started kind of my academic career in Boulder doing lattice QCD. For those of you in the audience who know what that is, you'll know that it's a very, very dark corner, sub-discipline of particle physics. For those of you who don't know what it is, you don't really need to know what it is. It is a dark corner of particle physics. And I promptly got out of that by A, spending a lot of time in the mountains, B, doing a postdoc in applied math, also at CU Boulder, developing numerical methods for partial differential equations, very much within the Python stack. And so it was really a few years of research, building numerical tools at the heart of basically turning the numerical Python stack from something that was seen as a toy and that people said was not viable into something that would be a real research tool. This was a bit of a miracle that I graduated because because I actually was fired by my advisor in my 5th year of grad school. Never a great career move if you think about it for a PhD student, especially if you're foreign in the US. But by the skin of my teeth, and we'll come back a little bit to how, with IPython, I did actually get out. After Colorado, I spent some time at Berkeley, originally working in brain imaging, oddly enough, so I've had a really bizarre career, right? What does a particle physicist do in brain imaging? I basically came to Berkeley to build open source tools for data analysis and functional MRI. And over the years, Berkeley got involved in the launch of a new institute called the Berkeley Institute for Data Science. This was back in 2012. I was part of the original PI team that built that. This was funded by the Moore and Sloan Foundations, where when funding began to appear for this kind of ecosystem, which had not been the case at all earlier, and that led eventually to me being now faculty in the stats department, actually recently tenured, so not assistant anymore, But in all of that, why geoscience? Why does this talk have geophysics in the name, or geoscience in the name, and earth sciences? Well, part of it is these pictures. That's actually what I love to do, and I had a lot of envy when I was in grad school and I was babysitting boring supercomputing simulations, and all of my geophysics friends were complaining that they had to go to Everest, paid for by the NSF, because they had to do field work that they didn't feel like, right? And that gave me a lot of envy. But number two, you may have noticed that the world is on fire in a very literal and heartbreaking way, and that climate change is probably the single biggest challenge that we all face, and hopefully I will spend the rest of my career building tools that not only help science at large, but that actually make a teeny positive contribution in the direction of helping the earth sciences. I am fully aware that this is a problem that has many dimensions, and most of them are social and political and not scientific. But hopefully we can contribute a little bit by giving the scientists better tools. Though the patterns of data and computation that we'll be talking about are actually applied to more than the geosciences, and so so there's still a lot of what we're doing that I think will have broad and generic impact. Geosciences are an interesting field that today is faced with the challenge that kind of the cycle, the virtuous cycle, if you will, between the development of theoretical ideas. Geoscience deals with the real world, with messy, noisy environments, but they're still driving equations, right? If you're modeling the ocean or the atmosphere, you have constitutive equations. You have the Navier-Stokes equation. If you're trying to interpret the behavior of electromagnetic signals underground, you have Maxwell's equations. And in a variety of problems, you actually have physical models. But you also have a ton of observations and data that come from the messy, noisy real world that go beyond what your models can capture. And historically, these have been fed into simulations, and there kind of used to be a little bit of a virtuous cycle where these three modes of thinking about the problem fed into each other. And many folks have been arguing that over the last few years, the gears of that engine are kind of grinding. The theory, the complexity of theoretical models is increasingly large. We want models that are more realistic, that are larger scale, that include more nonlinear terms, that include noise. The volume of data that is flooding the geosciences, same story as in virtually every discipline. I was just talking to Calvin, works here at CFA, talking about the kind of spectroscopic data that he's being flooded with in both astrophysical data and laboratory data. And the computational side and the simulation side has turned into a game where if you really want to make progress, you more or less have to become an AWS engineer. It's not a coincidence that AWS has a booth outside, right? It's not a coincidence that the cloud providers are here, because they want to talk to the scientists. But the problem is that a working scientist, a grad student, a postdoc, doesn't anymore have the time to really become a full stack cloud engineer while simultaneously being a very good mathematician, while simultaneously developing all of the statistical machinery to deal with terabytes of data per day, which is both a theoretical and a technical problem. So the flow between these three modes is really beginning to be a lot less fluid and efficient than it used to be, because and we're trying to really ask what can we do? What can we develop? What kind of systems can we build to help with this problem? To help getting these gears kind of turning again. In the geosciences, though, you can basically replace any domain field of your personal interest in the center here. We're starting to sort of have the intersection of not only the domain knowledge that we had before, but actually the need for a fairly sophisticated data science stack that includes actually theory about inference, theory about methods, theory about statistics and machine learning, but also a fair amount of what we could call data engineering, the kind of things that people like your AWS folks outside are very good at, and also a non-trivial amount of software. I mean, as Alyssa mentioned, IPython began its life as a little quick and dirty hack. It's turned into 18 years of my life, basically. And so I'm going to spend a little bit of time asking how can the scientific community build some of these things to help with this problem, so that everybody doesn't have to spend the next 20 years of their life only on one thing. And for that, I want to talk for a second about the fact that when we think about software, when we think about open source software in science, if you're thinking about a small tool that you're developing, the software maybe that matters. If it's a small project that only you and a couple of your colleagues use, the code, the software is really what matters. However, once you cross a certain scale, once you cross a certain level of impact and level of complexity, in a sense, the software is the least important part of the problem, and you really have to start thinking about other things beyond the software. And these are lessons that we've learned over the years with Jupyter. First is the fact that most people don't come to you because of the software. At least at this point with Jupyter, most people don't come to us because specifically of the software. What brings them to us is content. It's an idea. It's a textbook for data science that they need to use in their courses. It's a paper for which someone published notebooks that they want to read. It's an online course that develops ideas in bioinformatics or in the analysis of cuneiform tablets. There's a professor at Berkeley who works on Assyrian and does basically NLP and machine learning on dead languages and builds this kind of content. And so as a project, we have had to learn how to engage with a much broader community by developing the support for content, the support for services that actually take sort of the stories that people want to tell into the domain that people are interested in. And so that has meant building not just the software tools, but actually building infrastructure like NBViewer. If someone wants to share a notebook with someone else, they can tell them, well, go and install all these things, blah, 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 blah. Or they can tell them, just look at this link. And it looks like a web page. They can click on it on their phone. They can read it. NBViewer was a tool to share that was built to share notebooks with zero installation. Binder is a tool that we'll talk about again a little bit later that helps that level of ease of sharing carry on not just to reading, but actually to executing code, so effectively to making reproducible computations shareable. And so we've had to spend a lot of time kind of designing the infrastructure, designing the services, designing the machinery for reaching endpoint users. Now, below the software layer, because that's the one that as I said, that I'm skipping, it's kind of the obvious one. The code is the obvious thing. The other things that you have to think about if you want to have this kind of broad impact, and if we want to build the kind of ecosystem that we need today, is actually to ask of the software, what ideas does it embody, and how can you represent those ideas in a way that supports an interoperable ecosystem? And so what we've done with Jupyter is we spent a lot of time taking the core pieces that were there in IPython, which began as a Python-specific project, and ask, well, how could that happen for other languages? How could these ideas be applied to other languages? This actually began here in Boston, where some of you, who here has used Julia or at least knows of Julia? a few of you, quite a few of you. Not too surprising, given that it's an MIT product from next door. Wonderful language. And I was hanging out with some of Jeff Bezanson, one of its creators, at a conference here, at a SIAM conference here in Boston in 2012. And we started hacking on basically running the IPython engine, but with Julia as the backend instead of Python. And eventually, that work got turned into generalizing the protocol for how Jupyter communicated with its Python backend into something that could be used for any programming language. We flew the Julia team then to Berkeley the year after, and they spent a few days, literally while the IPython team was in one table, they were sitting in the table next to us, actually building the first running kernel that would make this engine. It was still called IPython at the time, but that would make it run with Julia as its backend. Then one of my postdocs went and worked with the R team at a meeting at GitHub in San Francisco a few months later in creating an R backend for it. And once you've done kind of n equals 2 or 3 with these kinds of problems, you're kind of in asymptotics, right? You've smoothed out the things that were too specific to one technical stack, and then you have a generalizable abstraction. And what we've done is actually create a standardized protocol for interactive computing, for running code in any programming language that has been adopted very widely, and that actually supports an ecosystem where others implement other things, where others actually build separately their own engines that then run against our stack. That takes time. It takes the time to think through these things. It takes the time to work with each of those communities. Not all of them, but at least you have to work with a few of them to smooth things out. It takes time to iterate, but it actually gives you impact, because now you are supporting not just what your software can do, but what others can do in their own stacks. And finally, it's not just about supporting interoperability at the technical level with standards and protocols. It's supporting the fact that software is written by people like you and me, by humans. And humans are messy things, complicated things. This is the hardest part of taking a project to the level of sort of impact and scope and development that we've done with Jupyter, is that you have to spend a ton of time on things like community management, governance. When Jupyter, when IPython Jupyter was a very small project, it was fine for basically a couple of people to answer things on a mailing list. If you want to engage with a company and develop a collaboration strategy, and they ask you, so who do we talk to? And you say, oh, I'll just send an email to the mailing list. Somebody will answer, maybe. That's not an appropriate answer. When we had, so Brian Granger, who actually did his postdoc here at the CFA, he's faculty at Cal Poly and is now actually working at AWS. He's been sort of my co-director in the project for a number of years. When Brian and I began effectively formalizing how to govern the project and actually writing that down, we had a meeting with IBM, who was interested in collaborating with us, and we could hear the sigh of relief at the other end of the line when they started asking questions, and you could tell that they were very uncomfortable about sort of what are these yahoos on the internet that we're going to have to talk to. And we send them a URL on the video link and say, no, look, it's written down. These are the governance documents. This is how this thing operates. We could see that they said, oh, okay, these people have it together. They've designed legal structures. They've designed fiscal sponsorship structures. They have machinery to operate as a proper entity. Guess how much of this kind of sort of management is taught in a PhD in particle physics? 0. But if we hadn't done all of this, and if we hadn't spent endless amounts of time building all of this human infrastructure, this project couldn't reach kind of the level of impact that it has today. It couldn't meaningfully interact with Google, with Amazon, with Microsoft, with IBM, et cetera, and with a very, very broad community of stakeholders that spans also industry, government, academic labs, individual contributors, et cetera. So what happens is the software, in a sense, is the easy part. We all like to write, at least many of us like to write code, and GitHub makes a lot of those processes easy. What you have to think about if you think about building tools for modern science is kind of the fact that with those tools, ultimately, we tell stories. As scientists, our stories are told typically in academic papers and increasingly through other media, but But basically, we have stories about the world and about our science to tell. Those tools should actually represent ideas that support ecosystems, ideas that are abstracted, and that hopefully will outlast you. At this point, for example, a lot of the core protocols that originally were implemented in IPython, there's honestly probably a better implementation built by some sort of Jupyter people, but from a startup in France that have now a native new C++ implementation of the core protocols that for many use cases is actually better than the IPython one because it addresses some low-level issues with threading and whatnot that make it more robust and more flexible and whatnot. It's a completely independent implementation of the core ideas, and that's what you want. And ultimately, managing and building the human substrate for a healthy community is what gives you both innovation and new ideas beyond what you would have, and resiliency. The diversity of a community, the diversity of stakeholders, the diversity of people in that community will give you resiliency as new things come along. Now, with this kind of machinery, more than just open science, and it's a bit of a cute nod to the FAIR principles of open data, we think that science should not just be thought of as something that is open, but actually collaborative, reproducible, and extensible as well, and not just open. By collaborative, we mean that we build tools that, yes, they may have begun as someone's, initially I told my advisor I was going to be gone for an afternoon. As Elisa mentioned, I literally disappeared. This was my second advisor. The one who had fired me had already fired me. This was the one who was rescuing me. And then, despite the fact that she was trying to rescue me, I tell her that I'm going to be gone for an afternoon, and I disappear for 6 weeks. This was the very, very, very first version of IPython was a 250 lines script, and you can see here still it has my, this is up on GitHub, it still has my, my colorado.edu email address, and Pi0 was the name of one of the particle physics servers, which is where we had our email at the time. But even from the start, IPython wasn't me alone, because that teeny little bit of code that I had written turned into that 6-week marathon because I was merging code of mine with code from a grad student at Caltech, Nathan Gray, who had written some other interactive tools for Python, and with code from an oceanographer, interestingly now a geoscientist, in Germany, Janko Hauser, who had written a different system called IPP, Interactive Python Prompt, for interactive computing in Python. And I took the codes from all three, I emailed both of them, I asked them if they wanted to collaborate, and they said, both said basically the same thing. No, too busy, but my code is open, do whatever you want with it, run with it. Go for it. And obviously, a grad student hiding from their advisor and procrastinating goes and blends those three codes, and that's what became IPython, so sort of 0.1 that was released in December 2001. But even that collaborative seed would never have gotten to where it is if it wasn't because we have built this massively large collaborative community that has probably in the thousands of volunteers at this point who have made contributions to various parts of the project, and stakeholders from academia, from education, from industry, from government, et cetera. This is a picture from one of our from our last kind of all-hands meeting in DC last year. We try to have one of these with the core, with folks from the core team, 20 to 30 people in the core team, who basically people who spend a lot of their time on Jupyter. There are people here who work at Google, people who work at Amazon, people who work in academia, people who work in industry, ex-CERN particle physicists. So we have a mix. We have a mix of stakeholders who have very different business needs, who have very different kind of reasons for doing what they do, and we try to build a collaborative environment where they all actually contribute to the same mission. When we talk about openness, that's in a sense the easy one in that it's one whose dimensions of openness we've thought a lot about. There's code, there's data, there's open access to publications, there's openness in the standards, the data standards, the technical standards that support interoperability. The projects like Jupyter and projects that embrace kind of this integrated view of open science can make contributions in all of these dimensions. But specifically going sort of to the next principle of reproducibility, this is an area where we think we can make important contributions. I'm sure many of you have seen this quote. It's been repeated ad nauseum. We use it in virtually every talk on this topic because it really captures extremely well kind of the point about not just sharing the PDF, the glossy brochure, the sales pitch of your ideas, which is basically what you get in Science or Nature, or whatever the preferred journal of your choice is, but actually capturing and sharing with others what will enable them to work off of your ideas. And that means, yeah, what you actually did. The code, the data, the computational environment. Importantly, at today's kind of complexity, the actual system where they can run your code. Because in many cases today, it's not just enough to give somebody a couple of scripts. The pipelines that we use today are complex enough. There's enough dependencies in there. There's enough things to install, to assemble, to stitch together, that if you simply tell someone, well, this is what I did, here's my scripts, that may not actually be enough. So in order to kind of meet this vision of reproducibility in computational research that Buckheit and Donahoe expressed back in the 1995, fairly eloquently, projects like Binder have come out. Who here has used Binder for something? Some of you. So for those of you who haven't used it, let me tell you a little bit what Binder is. The idea behind Binder is that if you give it the URL of a repository on GitHub or other publicly available Git repo, but most people use it with GitHub. And that repository, all you have to do is have a repository that follows basically some good practices, right? That repository has two things. It has a collection of notebooks that you want to demonstrate to run the code. And it has a file, which can be actually in a variety of formats, that says, these are the dependencies this code needs. This is what this code needs to run, which is something you should be doing anyway. You should be telling people what your code needs. But you write it down in a machine-readable format. You don't just write a README file full of verbose instructions. You actually put a machine-readable version of your dependencies. That is sufficient for Binder to go and grab that repo, clone it, install those dependencies, bundle it up, put it in the cloud, put it on Kubernetes. We now have, I believe, Google, a French cloud provider called OVH, On Vous Héberge, the Turing Institute, and I'm blanking on the fourth, all provide cloud resources for that container, for that repository, now turned into a Docker container to run in the cloud for you. So you put in goes the URL of your repository, and as long as that repository sort of follows good practices, out comes a URL that you can share with your colleagues, you can post on Twitter, you can share with your friends, that they can click on, and they will be running live with your code and your data on a free virtual machine now. Small one, we will not give you like a massive cluster for free, but it is actually a real machine where you can run real code. This has been very, very empowering. It's a project that was started by somebody at Genelia Farm, who's now at Chen Zuckerberg, and has continued with folks from the Jupyter team and the community over the years. For us, it was incredibly satisfactory, and as a physicist, this was amazing to me that back when the LIGO collaboration published the first paper of the discovery, the first observation of gravitational waves back in 2016. This was the first event, that merger of two black holes back in September of 2015. They published together with a paper, together with these figures that, by the way, were all made with the scientific Python stack, with NumPy, with SciPy, with Matplotlib, the kind of stuff that 10 years earlier people were telling us, stop working on this, it's a waste of your time, it's a waste of your career, this isn't real work. We were now seeing it in basically what's going to be one of the most cited figures in physics probably for the next decades to come. But that team also made available the Jupyter notebooks that ran all of this. And any of you can click on that URL, and you will be running on your phone, on your tablet, off of Binder, a repo that has all of the gravitational wave data from the LIGO collaboration, and you can rerun the analyses. And I know of people who have even gone and challenged some of the noise assumptions that the LIGO collaboration made by basically being able to run these codes and begin kind of asking statistical questions, which is exactly what people should do. I'm assuming that they know what they're doing, but it's perfectly appropriate that people are able to actually jump in, replicate, and then begin questioning the statistical processing of the data. But in addition to this idea of just reproducing and re-executing others' code, we want science to actually be extensible, meaning we want to build tools that others can build upon. And so in Jupyter, we kind of embrace that idea by trying to make everything we do as modular and as reusable as possible from an architectural perspective. And that's a different kind of thinking that is not thinking about our papers, about our endpoint, but rather about how we enable others. JupyterLab is kind of our reinvention of the user interface of Jupyter from the lessons of the last few years of usage. It's been a huge team effort with many, many participants. And what we did was try to build a system that would still offer the same notebooks that many of you have used, but actually on a software stack where the components of that, the idea that you have documents, that you have things that do computation, that produce outputs that can be visualized, all of those pieces are actually decomposed sort of as Lego blocks that you get to assemble and reassemble in any way you need. So you can still have notebooks, but for example, you can say this output of a notebook, I want to hold it here in a separate view, and as you do computations in one view, that the output of those is automatically synchronized elsewhere because these things are actually talking under the hood, because all of these things have now been sort of assembled for you as reusable components that you can wire together in any way you need. Maybe you don't want to have a notebook, but what you're editing is a markdown document or a LaTeX file or some other format, but you still want to do computations on it. So you can, for example, say, I have this particular markdown file that I can render here while I'm working on it live, but I'm actually attaching a computational engine to it called a console. This is not a notebook anymore. It can be a document in any format, but you can say, please connect a Jupyter computational component to this document so that while I'm developing this document, I also have computations attached to it. Data is now a first-class citizen. In JupyterLab, you can open images, you can open CSV files, but you can develop your own custom data viewers so that, for example, if you open this particular type of JSON data, which is GeoJSON, if you open it as plain text, it looks okay, like a bunch of curly braces. That's what JSON looks like as text, curly braces everywhere. But this JSON data type obeys a schema for representing geospatial data, which is more naturally viewed on a map. And so if you have the GeoJSON plugin, that same file looks like this. This one will happen to be museums in the DC area, right? The locations of a bunch of museums in DC. The point is we've built within this architecture the notion of custom data viewers as first-class citizens. The moment one of these viewers is available, you can also use it in your notebooks, you can also use it in your code, you can also use it as part of the rest of the system because all you've done is expose another view in the system, wrap, and most of these things are not new code, it's wrapping some third-party viewer that existed for that particular file format. So people have wrapped viewers for brain imaging data, for bioinformatics data, for solar physics data, for all kinds of things, and they can be used both for in kind of a GUI-driven browsing way for looking at data, and they can be used programmatically, which is very important that everything we do should be part of the computational architecture. A few months ago, I was visiting Colombia and met Aurel Lazar, who's a neuroscientist there, whose team had built this thing called the Fruit Fly Brain Lab. It's a bit of a tongue twister, which is a system that they built that exactly embraces this idea. So very briefly play this video. It has Jupyter notebooks. It's a custom JupyterLab interface. But now it has an anatomical 3D viewer for data from fruit flies. And when you select a neuronal circuit in the fruit fly brain, they can run a simulation of that as an electrical circuit, which runs on a GPU cluster that simulates the electrical behavior of that anatomical circuit. But there's also a custom genomics data browser connected to that particular circuit where they can browse properties about. And at this point, I don't know what the science is. But the point is, they have custom tools. This is an unmodified, the shell is the same JupyterLab that any of you can install with Conda or pip or by downloading the software. But they've added components for their domain. In JupyterLab, we ship a CSV viewer and an image viewer. OK, everybody needs CSV and images. That's a common data type. We're not going to ship an anatomical viewer for fruit fly brains or a genomics database browser for their format. But they get to build that. They get to build those components, and they get to assemble a domain-specific scientific environment where they get to reuse everything else that we had and now to add their own components. And this was exactly the vision that we had when we thought about the extensibility part of the platforms that we built. Now, once you begin building extensible infrastructure that supports collaboration, that supports reproducibility, it turns out people like it. And there's a country up north that has weird things like mass transit and healthcare. We don't know about that here, but they do. And so they think of infrastructure, right? And so what they've done is they've built, based on Jupyter, computational infrastructure from kindergarten, close to kindergarten, or at least elementary school, through supercomputing research in Canada. So any scientist in Canada who has funding from the National Research Council in Canada has access to a project called Syzygy, which is basically Jupyter on HPC resources managed by Compute Canada, which is their national supercomputing infrastructure, and it allows them to have access to basically Jupyter deployed clusters on their supercomputing resources. And together with, and this effort has been led by the Pacific Institute for Mathematical Sciences, Jim Colliander and Ian Allison at UBC. But they've also partnered with Cybera, this company, which is a nonprofit in the province of Alberta that has deployed Jupyter hubs not for supercomputing research, but instead for K through 12 educators, together with resources for curriculum development, so that educators can develop basically culturally and age-appropriate content for teaching math, for teaching geometry, for teaching various disciplines to their students, with them providing kind of both the hosting, the infrastructure, and the content development, which is really where the hard pedagogical questions are. In this case, the technical part is the easy part. The hard part is the pedagogy. But the point is they now have this kind of as a consistent national effort of infrastructure, and this began in Alberta, but my understanding is that this initiative is now expanding to other provinces in Canada. And then companies also adopt these things. At this point, Google, Microsoft, AWS, IBM, all of the big tech firms, and smaller firms also like CoCalc and CodeOcean and Anaconda and many, many startups have not just users of these tools, but they actually have shipping product that uses this machinery. So by making these things truly interoperable and truly extensible, we actually engage also with industry. Now, that's a tricky conversation. The ways in which industry can contribute back to the scientific stack, I'm still squarely kind of anchored in the questions of science, and the way in which we engage with these industrial stakeholders is a tricky conversation. If any of you is kind of in the space of reading blogs about open source and industry and whatnot, not just blogs, there was a very, very good article at the front page of the New York Times a few weeks ago about this, and about mostly about Amazon's role in that space. It's a complicated conversation. It's a delicate one, but at least we have a seat at the table. We are engaging with them. We are talking to them. And I think it is important that these tools also have industrial impact. In research and education, which is what matters to me, as I mentioned, the real driver of impact is when you put these tools at the communication endpoint, when you tell the domain story that people are actually interested in. We're seeing that at Berkeley with our data science curriculum. This is really what has driven the change and the adoption of these tools for us at Berkeley. If any of you have been to UC Berkeley at some point, you may recognize this as not a classroom, but the Opera House. That's Zellerbach Hall, the performance art complex. We have to borrow that for the opening day of class of Data 8, our Foundations of Data Science course, because the students don't fit in any classroom on campus anymore. And so we shove them into the Opera House for the first day of classes. We tell them what to do, give them the YouTube URL for the rest of the lectures, and tell them not to come back because we can't fit them anywhere. And so most of them, on average, don't come back to class because the classes are held in this classroom, the biggest one we have on campus, but that only fits about 750 people, about half the class. So they physically can't all come to class. But these courses that are the fastest growing courses in the history of UC Berkeley, Data 8 is called Foundations of Data Science. It's accessible to first week freshmen from any major whatsoever, with no computational requirements, with no math requirements, with no statistical requirements, with no programming requirements. And it's still a very, very intellectually very, very carefully designed and very rigorous course on the ideas of how to think and reason about data and how to make statistical inferences off of real data. Data 100, Principles and Practices of Data Science. I haven't taught Data 8, but I've taught Data 100 a couple times, is an upper division course that does have both mathematical and computational requirements. And then there's 2 more courses in this kind of course sequence of we have a new major in data science. One is called Probability 140. And just last semester, Mike Jordan and I finished teaching Data 102, which we call Data Inference and Decisions. It's a brand new course. We were just running the pilot. So this one is very, very fresh. These are very, very mature by now, and so is Prob 140. These 4 courses are hosted on Jupyter hubs that are available to the entire campus community that anyone can access. They're textbooks. Well, this one doesn't quite have one yet, but the others have textbooks that are visible online, that are accessible, and published as Jupyter books, and that anyone can run by using binders. So our students have real kind of internal access to them on deployed Jupyter hubs where they can do their homework. These things are persistent through the semester. And the rest of the community can not only download these things, but actually run them immediately by using these binder resources. So this ecosystem, all of these pieces kind of play together to drive this kind of impact. In research, it wasn't just LIGO. As it turns out, recently you may have seen the image that made the rounds of all of the front pages of the newspapers in the world last year. The first direct observation of a black hole by the Event Horizon Telescope collaboration. When these folks published their actual papers, they directly credited the numerical scientific Python ecosystem. NumPy, SciPy, Pandas, AstroPy, Jupyter, Matplotlib were recognized as explicit contributions to this really, really kind of major scientific result. I had a chance to speak with Katie Bouman at an event at EPFL in October where she was presenting some more details of their work. And one of the things that was really wonderful to see was when she took a moment to say, we actually analyzed the contributions, in a sense, the technical co-authorship of the stack that we ended up using. This was done in collaboration with GitHub. People at GitHub had to kind of write a custom searcher to let them analyze the dependency tree and assemble the contribution list of that dependency tree. But they basically tallied about 23,000 contributors to the entire scientific Python chain of tools that feeds into the tools that they actually used. And so this is effectively the community that has been built over the last 15, 20 years, and that is now beginning to be recognized by sort of the leading scientific results of our day. Now, getting back to the idea that we're trying at Berkeley to put a lot of this into the geosciences, my colleague Lindsay and her colleagues from UBC have been leading the development of a stack for solving inverse problems in geosciences. We don't have a ton of time to get into the details of this, but it's basically a multi-physics code to do inference and to solve inverse problems with geophysical data collected with a variety of physical modalities. It could be magnetic data, it could be gravitational data, it could be electromagnetic data, solving inverse fluids data, solving the constitutive equations, and do inversions to try to estimate the actual physical parameters of the subsurface. And this code is connected actually to an education. So this is a research, very much a numerical research code. It's basically a PDE inversion code. But it's connected to an educational effort where a stack of very, very rich interactive materials have been developed using Jupyter, using widgets to allow people to explore these parameters, both in a research context, when researchers are just trying to understand. I mean, we're working on a project right now on trying to basically apply machine learning to questions of representing the effect, what the right way of representing very, very thin but very highly conductive structures in the subsurface would be. And for that, you really need to kind of understand what the currents are doing, explore what the physics is doing. It's absolutely wonderful to do that with interactive controls that are designed for that specific physical question and which the scientists can design. You don't have to wait for a software engineering team to build you the graphical tools. And that, once you've built that, that can be carried over into education. So that stack is part of a project called geosci.xyz that builds educational materials for geosciences using these research tools and that are deployed as a collection of Jupyter notebooks and that have been used in a variety of geosciences courses worldwide. Now, this is part. Now, in the geosciences, Jupyter is now part of a larger project called Pangeo that some of you may have heard about. The image in here is just a Jupyter notebook with somebody zoomed on an image. You see some color bars at the bottom, and then the image gets a little bit more refined. What's the big deal, right? I mean, you zoom in an image, it was blurry. After a couple of seconds, it's not blurry anymore. Well, the trick is that make the image not blurry required wrangling about 100 gigabytes of Landsat data scattered on a cluster that covers all of the entire state of Washington. What the scientist wants to do is to zoom on their image, right? They just want to zoom, and they want to see the fine resolution data. They don't want to become a cloud engineer. They don't want to become a Google or AWS or Azure engineer. That's what Pangeo does. Pangeo is the project that basically answers that question that we posed at the beginning of how do we get those gears turning again. In fact, that metaphor is from the Pangeo team. The Pangeo team put together Jupyter as the scientist-facing endpoint, together with a tool called DAS for distributed computing, together with Xarray, which is basically NumPy meets Pandas for scientific data model, to try to give an architecture where people can explore these massive amounts of data that we have now, combined with large-scale simulation, but with the convenient interface that they're used to without having to become themselves a cloud engineer. This pattern is absolutely wonderful, and we're now collaborating with this team. I can get into the details of that in the questions later if anyone is interested, because we don't have time, too much time right now. But the point is that this notion of building tools that allow a scientific community to explore mountains of data, where different members of the community may bring different parts of the data to the problem, or may be interested in different aspects, is a pattern that is happening everywhere. And Pangeo is being very successful at basically building tools that actually enable that little engine to turn again. We partnered up with Joe Hammond, who's one of the Pangeo leads, and together with Laurel Larson, who's a hydrologist at Berkeley, we partnered up with them. And actually the NSF, Pangeo is funded by the NSF, by the way, by EarthCube. And they just funded us recently for another project that combines 3 use cases, oh, that D was a typo, 3 use cases in geosciences, together with the development of more Jupyter machinery, precisely kind of in the Pangeo stack, and where the NSF actually agreed that these 2 things should be first-class citizens. It's not about we're going to build infrastructure, wink, wink, nod, nod, we'll pretend that we're doing science, but nobody cares, or the opposite, which is we're just going to publish papers, and we will talk to some computer scientists who will build something. No, this was a case where we said these 2 things will actually, often the same people will be working on both sides, and they will be treated as co-equals in the project. The NSF went for it. We're also working on building tools for a new satellite that NASA put up sent up in 2018 called ICET-2. It's a LIDAR instrument optimized mostly for the monitoring of ice, but not only ice. And we're trying to build kind of an open stack for the analysis of these data deployed with Jupyter and the Pangeo machinery called IcePix. If anyone is interested here in cryosciences, I would encourage you to go to our next Hack Week in June, where we're going to basically be continuing to build this machinery. And in the geosciences, it turns out that we went to AGU, which is the big geoscience conference that happens every year in San Francisco, and there was a raft, including a Jupyter. The title of this talk is a little bit hard to read, but it was Jupyter with Jupyter. That was very neat, from a planetary scientist at UMichigan who actually is working on Jupyter the planet with Jupyter the tool. But there were a lot of people. This was not organized by us, and there were a lot of people in the geosciences who now have embraced these tools as the machinery both for research and for education in their context. Now, very quickly, I'm going to kind of flash through the last part of this, which is the less optimistic one. It's great. You're an academic scientist. You love these tools. They have great impact. Jupyter has been successful. We've gotten funding, resources. What's not to like? Well, William Stein actually did his postdoc here at Harvard. Number theorist, graduated from UC Berkeley. Right off the gate, he got tenured faculty offers at the top math departments in the country. And recently, well, last year, published this blog post where basically he said, I can't keep building open source tools for mathematics the way I am. I've been on unpaid leave trying to start a company that actually uses Jupyter for many things. And my unpaid leave is up. I have decided to resign. This doesn't work in academia. Traditional software infrastructure funding in the sciences has this pattern of keep building a new version of the thing that actually doesn't do anything, and just keep doing it. And as long as you can get another CS conference paper, you're good to go. The CIC directorate will keep giving you money. And we now have 10 different ways of getting 80% of the way, and not one that actually works. The Pangeo people are really kind of trying to break that pattern by embracing this notion that you reuse things, you configure them for a specific use case, you contribute back upstream, and you actually collaborate across disciplines, and kind of the traditional metrics be damned. If this is of interest to you, I highly recommend that you just Google that term, and they wrote a blog post where they kind of flesh out this idea very, very carefully in one of the recent blog posts, because I'm trying to wrap up here. But the issue is basically that these incentives of open collaboration that I've been talking about that exist quite a bit in these open communities that I've been a part of, in most dimensions, clash pretty badly with our real jobs. I mean, I'm faculty at an R1 university, right? These are the metrics that my university tells me I have to honor, and this is what the world I live in kind of actually does. And maintaining a dialogue across this boundary has been the last 18 years of my life, and I can tell you, it's not an easy one. It's kind of quartered and drawn, medieval quartered and drawn is the metaphor that mostly comes to mind. So I'm going to wrap it up there. I want to thank the local team at Berkeley that I work with, at UC Berkeley, at LBNL, at NERSC, and even in industry at Bloomberg, who are, because the broader community is too vast for me to have pictures of. And I just want to leave here as kind of food for thought, this notion that in the earth sciences, though this Pangeo pattern, we're actually trying to organize a workshop for other scientific communities. There's a Pan-Astro, there's a Pan-Neuro, there's now other scientific communities that have similar use cases, but that these patterns of open collaborative science are actually something that we should continue to push for. Despite my somewhat pessimistic slides at the end, this is a conversation that I'm willing to continue to push for, and that I think we should all keep working on, both within academia, with industry, and with the federal agencies. Thank you so much for your attention.
Thank you, Fernando. Excellent talk. We have time for questions.
You'll tell me when to stop.
Just shout my question. So you finished.
I'll repeat the questions.
You finished on a note that pretty touches a nerve, I guess. What do you think needs to happen for academia to embrace, the culture that open source embodies? Like, academia counts things by H-index, by citations, and that kind of thing. Whereas for open source software, tracking usage is not such a trivial, and tracking adoption is even less trivial. Like, what do you think needs to happen, or what kind of discussion?
So the question is, what needs to happen for academia to recognize some of these things as part of the real job? And that's indeed kind of near and dear to my heart. Effectively, I was a litmus test of whether that could happen or not, whether I got tenure at Berkeley or not. I was hired actually in stats in 2017, and I was up for tenure 6 months later. The deal was that I would go up for tenure immediately, and my case was solely built on this. My CV is a mess. My CV is a complete mess, right? By any traditional metrics, nobody in their right mind would hire me. And now I am actually trying, I am writing tenure letters. I'm writing recommendation letters. I'm working on cases. I'm working with UC Berkeley on trying to basically flesh out how to think of what the intellectually equivalent criteria should be to the traditional academic metrics, where it's not about lowering any intellectual bar, but it's about understanding that the dynamics of contribution here are different, the dynamics of participation and collaboration are different, and how can we look at those things in a different way. It's a very long problem to give you kind of a very quick answer, but what we're trying to do is actually build a record of cases that have actually successfully done some of this, and design criteria that are a little bit, they need to be a little bit more flexible, but precedent does exist. There are disciplines that go beyond counting papers, right? Not every discipline is as paper counting as some of the sciences. And I think it is possible to build a portfolio that is sort of multidimensional, and you may not have a single metric to optimize, and I would argue that's a good thing, that you don't give people a single metric to optimize, but instead you give a menu of ways in which impact and intellectual value can be looked at, and based on which cases can be built. Now, there are countries and institutions that are very, very, like, literally impact factor counting oriented. Honestly, I think those places are lost. I think that is such an fundamentally broken approach to the problem that I don't know how to fix that. Like, you need to change that first. But places that are willing to look at something with a bit more nuance, then I think one can build an intellectual case. Paulo, I'll let you. Is that a microphone?
Test mic.
Oh, wow.
Coordination.
Awesome.
So, Fernando, thank you. That was a great talk. I agree completely with what you just said. I also need to tell everybody that you did get tenure, and I introduced you off your wrong website that says you're an assistant professor. You're an associate professor.
I am. I should update that.
Anyway, right. But the question is, it seems like everybody in this world knows about Jupyter and Jupyter Notebooks, and before that knew about IPython, and you said how important it is to build a community. And I'm just curious what you think the most important tool or tools were to kind of get the word out about what you were doing, and how did this kind of catch fire? I mean, Jupyter is incredibly useful. Other things might not be as useful, but there are very useful things that people don't know about. So how did you do it?
I think it was, we can't take too much credit for it. I think there was a coincidence of timing. I think part of our success was being at the right time at the right place. Yeah, we did a lot of hard work. We did a lot of hard work quietly with like sublinear growth for a decade. And then we were, around 2012, we were there at the right time at the right place. We built the notebook after the version of the notebook that everybody knows about is like the 5th prototype. We had many failed and dead-end attempts. Brian and others and I worked on earlier attempts that failed. So by the time we got it working, A, we kind of got it right because we had done it wrong 5 or 6 times already. And B, the rest of the data science ecosystem was exploding, right? Pandas came on the scene. The scientific Python ecosystem had matured enough that it became viable to do a lot of really interesting things relatively quickly and effectively without too much pain. That's number one. And then the second thing that happened was, I mentioned NBViewer. NBViewer was another one of these kind of weekend hacks. It was somebody from the community. I mean, he's now a core Jupyter member, but at the time, he was a grad student in physics in France who over a weekend wrote this baby web app put it up on Heroku that said, well, Jupyter has tools to convert notebooks to HTML. I'm going to put that as a service so that you can convert anything. That had a huge impact because what happened was people began tweeting. People began grabbing their notebooks and saying, I did this thing, here's the link, you can view it. And those things caught fire. Peter Norvig from Google, very famous AI researcher, began blogging. What happened was we began seeing that NBViewer would crash. Whenever Peter Norvig would blog, his blogs were notebooks. He would just write a notebook, put it up, and his blog was just a simple web page with NBViewer links. Every time he posted something, it went viral in the computing circles, and we got, within 24 hours, months worth of traffic, which crashed, because at the time it was on a free Heroku plan. It completely crashed everything. And so these kind of social network type effects, combined with the right tool for sharing at a point where the ecosystem was just mature enough for people to do very interesting things that before were not possible, I think was the perfect storm, right? And I think it was a combination of these factors of timing and virality that all of a sudden, I think the community was thirsty for this, and we managed to be at the right time at the right place. That's the best I can think of.
I finally figured out what the catch box is. So I have a comment, but I'll turn it into a question as well. I work in speech. Early in your early slide, you had this virtuous cycle with theory and data, so with theory and ideas, observation and data, simulation and computation. Well, in speech, we don't have any theory. And I think in data science, you generally don't have any theory. It's all observation, data, simulation, computation, and even the simulations are often pretty minimal. So my question is that something that academics should try to fix? Or should we just admit that many of the areas that people are doing data science in now, there's no theory, that's life?
Well, that's a complicated epistemological question. I'm still a theorist. I'm still a physicist. I still do believe in theory. There is a lot of data science where there is theory, and I think the interesting challenge is now how do we combine effectively and in a principled way statistical learning tools with first principles, whatever the definition of first principles is in a given discipline. So it is true that data science as is understood in industry, there are areas where it truly is sort of completely theory-free. If you're just trying to classify the purchasing preferences of your customers on Amazon or on Netflix or something, that probably is truly theory-free. There are other areas where people still do build some types of models, and the interpretation of those may be something that still matters for a variety of reasons, right? The interpretation of those models may still actually be important to have an intellectual discussion in that field, even if those models are not Maxwell's equations, even if they're not Schrödinger's equation, even if they're not sort of first principles equations. However, some of that problem of that engine is technical. And the technical challenges of analyzing, even if you are in a very theory-free world, the notion that the domain folks working in that field shouldn't be burdened with effectively becoming professional software engineers plus Google infrastructure engineers plus data management people, that remains true, even absent this epistemological little sidetrack. And I think for that problem to ease the fluidity of those disciplines, stacks like these and infrastructure and community approaches like these remain valid just as much and they remain just as important.
All right, so I think we should take another game.
Thank you very much for your attention.